So yeah, everyone, again, thank you for joining us. I know there's a few people trickling in as well. So in the meantime, there should be a poll that has popped up for you where you have like a few fun questions that we're just curious about learning more about, who is attending and sort of what you know, what you don't know. And but at the same time, if you do have any questions or comments, there is a Q&A that you can type in any questions or comments. We're happy to answer that way. And we will likely save a lot of that part for the end. So we'll go through some of our slides, and then I don't know if you can see all the panelists here, but we do have Katie, our champion, who's actually on campus and inside of the clean room already. So she's ready to go, but we want to make sure we have some time to like give you some background knowledge in case, not everyone may or may not know about nanoscience. Okay. And we're really excited. I think this will be really fun. Okay. Let's see. We'll give it maybe 1 or 2 more minutes. I'm glad everyone is using the chat to say hi. I think that's really fun. So please feel free to do that. Okay. All right. Well, I'm about to end the poll. So if anyone wants to add any more pieces of information, please do. So there's 34 out of 43 people who have voted. So if you haven't already, please make sure to do that. Otherwise, yes, we will get started. We were waiting. Thank you for asking, but we'll get started in just a minute. All right. Anybody else voting? Otherwise, we will close it out, and then I'll share the results really quickly. So most people have heard of a nanoscience. And what is a wafer made out of? Although we all wish it was a cookie, most wafers are made out of silicon. We have we have a really nice mix of people that are interested in STEM, so some chemistry, but engineering is the most popular one. Then I think the next one is computer science, some physics, biology, a little bit of math and chemistry as well, so very cool. How clean is a clean room? I thought this was a good question. Options above compared to after a bath or a clean as a whistle. And most people are coming from East Bay. Okay, very cool. All right, so what we're gonna do is get started. So thank you everyone for coming. So we are here at Stanford, or more like in the area of Stanford. So I'll introduce myself and then I'll introduce my colleagues that are all Stanford affiliates. So my name is Angela. I run the education and outreach programs at what we call Nano at Stanford, which is a collection of facilities across the campus, mostly in the science and engineering quad. And you can see me here, and this is one of the clean rooms that we have where I give a lot of tours. I work with teachers and teach people about nanoscience. And I have always loved science. Here is a picture of me at the American Chemical Society. My background is in chemistry from UCLA. So if anyone is a Go Bruins or the LA area. And I always loved chemistry and just have always been interested in science. And later in life, I kind of translated over to talking about science rather than doing the research. And then for fun, I always love a good theme party. So I like to dress up in all different costumes. So like, for example, October 31st is coming up. So I'm trying to live vicariously through trick-or-treating online, I guess. So that's me as a pizza. Okay. And then I'm going to hand it over to Grace.
All right. Hey, everyone. My name is Grace, and I am a current senior undergraduate at Stanford University. I study material science and engineering, and I'm also doing a master's in computer science. And throughout college, my work has been a lot on making printable batteries. So you can see down on the bottom left, there's like a low-cost scanning electron microscope that I'm hopefully designing my battery to help power. In the middle, I've done a lot of 3D printing in my time too. So on the bottom, you can see some of my 3D printed pots with some cute plants. And this past summer, I really got to dabble in aerospace I interned at SpaceX, so made some adhesives to help fly future rockets and spacecrafts. And on campus, I also helped fly high altitude balloons with the Stanford Space Initiative. So yeah, looking forward to meeting and talking to you guys today.
All right, hello everyone. So my name is Katie, and as you can see, I look a little bit weird, but I do look normal sometimes. So my work is mostly based on ultra-thin transistors, which I'll show you a quick picture of back when we go to the cleanroom tour. I chose to study science because I think science is like a little craft, and sometimes it has a little bit of danger to it, which is kind of fun. And then for fun, that's our family dog, Roxy, a German Shepherd. And then our research group also likes to take funny pictures from our samples and make them into little cartoons and graphs.
Awesome. All right. And then we have Ben.
Hi, I'm Ben. I'm kind of an old timer compared to you guys. I got my PhD from Stanford in 1998, and I've done a lot of different career jobs since then, mostly in research, both for large corporations and small startups. But right now, I'm actually with UCSF, which is a medical school. I'm not a doctor or a physician in that sense, but I work in the artificial kidney group, and I help with the team to make micro mechanical structures to enable the artificial kidney to work. And I'll talk more about that later. And for my interest, as you can see, me and my wife are big cat lovers, and we also love to travel, although not this year. Thanks.
Great, thank you. And then, yeah, just a quick reminder, I actually turned off the chat function just so we can focus on the presentation. But if you do have any questions or comments, please use the Q&A as something where we can sort of sort through all the information. And then at the same time, we will probably save most of the questions if we can't answer them live at the end, okay? All right, awesome, thank you. All right, so I wanted to briefly talk about nano, right? So what is nano? How small is nano? I think most of you have already sort of gotten a sense of what it is, so I won't focus too much on it, but it comes from a Latin word called nanus, which also means dwarf, right? And it is, this word nano really operates as a prefix to indicate unit multiplication. So 10 to the negative ninth, which is 1 billion, right? And so we typically use that in a length scale. And in the science world, we use meters, which is about, 3 feet in width. But for a nanometer, it's 0.000000001 meters is 1 nanometer. Okay. And so what does that mean? What does that exactly entail, right? So we have sort of a general a scale of just giving you a sense of what big or small things are. So if you take a look at your own hair, right, if it's easily accessible to you, you can take a look at your hair, and that is about 100 microns in thickness. So micron is 10 to the negative sixth, and nano would be 1,000 times smaller than that, right? And so if you go here about 10 microns, that's the size of a cell, and you are comprised of billions of cells. And then smaller down here, which is where we're going to focus on, is 10 to 100 nanometers. And that's really where things kind of happen at the nanoscale, what we consider the nanoscale that's really important. And that would be basically 100 times smaller than your cell and about 1,000 times smaller than your human hair. And then if you go even further, there's all different types of things that are smaller than nano. So like proteins that make up your body or your cells actually, even small molecules, and even going down to atoms. Okay, all right. So another way to think about nano is that you can describe it as your fingernails, right? The things on your hands, they grow about 1 nanometer per second, but you only cut your nails maybe once or twice every 2 weeks, right? So very small. A seagull, I think this is a fun one. If a seagull landed on an aircraft carrier, one of those big boats that carries like planes and things like that, would sink by 1 nanometer. And again, your hair is approximately 80,000 to 100,000 nanometers wide. And then a strand of human DNA is about 2.5 nanometers in diameter. Okay, and actually I'm looking, I'm gonna wait for some of these questions, like the CRISPR question we'll answer at the end. The ultra thin transistor, I'll also let Katie answer, but I can read it out later. And then why do they use nanometer? That's a great question. Nanometer is just a way to indicate the size more very quickly, very easily, whereas if I said 1/1000th of a meter, that would make it a little bit harder or wordier to say, right? So in the science world, when we talk about nanomaterials, it just means, you know, it's an indicator saying, okay, this is the scope or the size that we're working on. Okay. All right. And then, oh, one more fun thing is that if the world was 1 meter wide, right, 1 nanometer would be a marble that you can hold in your hand, which I thought was a really cool example as that. All right. Okay. And so I'm going to actually hand it over to Grace to talk a little bit more about, you know, what nano means and why do we care about it and why it's so special it is. Okay.
All right, great. So when you think about nanoscience, sometimes you'll imagine, let's say, gold. Usually when you think about gold, it's like this bright yellow color, something that's, wow, very expensive. But at the nanoscale, when you shrink it down to, say, nanospheres or other nanomaterials, the way that the gold actually interacts with light is very special. It's known as kind of the quantum effect, and at these small scales, gold nanoparticles actually reflect light to be a reddish to violet sort of color based on their size. And long ago, architects and designers actually didn't know the nanoscience behind it, but they were able to use these small nanomaterials for designing stained glass windows. On the right, we have the rose window, which is very famous dome in Notre Dame. And in Paris, people go to visit it and see the many different vibrant, vivid colors. And these vibrant colors are actually a result of the way that nanomaterials reflect light. So we have a question for you guys now, and we're going to take a poll. What melts faster, the big chunky ice block on the left or a bag of crushed ice on the right? Great, these votes are trickling in.
We'll give it a few seconds more. Most people have voted, I think. Okay, so I will end it and share the poll. Okay.
All right. Yeah, and the vast majority of you guys are correct. The bag of ice will actually melt a lot faster than the huge block of ice. And this is because when you have ice cubes that are very small, there's a lot more surface area. So they're able to interact with the environment more, and the ice cubes are able to thus melt faster. All right, so we'll close the poll now. Nanomaterials are very interesting to make. In general, they can be classified into 2 different categories. First, the top-down approach is like how sculptors or other artists make these vast, really intricate designs. They usually start with like a big block of stone or a big chunk of something, and then maybe work at it downwards. So they'll use a hammer or a chisel and then kind of mold the part that they want to make, such as a sinker here in the middle. Meanwhile, there's also a bottoms-up approach, which, if you think about like Legos, is all these individual building blocks that can be used to make very large, more complex designs, such as houses or spaceships or other things. In material science, a bottom-up approach can be very useful, say for 3D printing, when you're using small molecules such as carbon, hydrogen, oxygen, nitrogen, other things to build upwards. And this will perhaps pose a more sustainable solution than the top-down method, where sometimes you have a lot more waste. So for a lot of material scientists, chemists, biologists, we have this really advanced nano toolkit that allows us to visualize materials at the nanoscale. So first, for fabricating and synthesizing nanomaterials, we have equipment such as photolithography and the etcher machine, which is often used for fabricating silicon wafers and printed circuit boards, for example. In the middle, to be able to actually see the nanomaterials, we use very high resolution microscopy methods, such as the scanning electron microscope, the transmission electron microscope, and the atomic force microscope that allows us to determine the surface topology of the nanomaterial. And on the right, for applications, all of this work can go towards so many different interdisciplinary fields, such as photovoltaics or solar cells. These nanomaterials can be used for cancer detection, such as MRI imaging. And recently, researchers have also been able to use nanomaterials for small writings. So here in the Spirit at Stanford University, researchers are able to create the two initials, S and U, at a very small dimension. So now to compare and give a sense of what's the difference between a normal microscope and a scanning electron microscope, here we have a radiolarian, which is a very small single-celled protozoan that's found in the upper levels of the ocean. On the left, if you use an optical microscope, one that you might have in your middle school or high school, and that you commonly use in biology classes, you'll be able to see just a surface level, just kind of blurry image of this radiolarian, which actually kind of looks like a Yoda head, so that's pretty cool. But on the right, with a more powerful scanning electron microscope, which uses electron beams instead of light to image the microorganism, you can actually see a lot higher resolution photo, and there's much better depth perception as well. So this allows you to image the surface of nanomaterials with a high degree of precision and accuracy.
Okay, so we're going to, thank you, Grace. We're going to hand it over to Ben. One quick question that I had, I'm going to answer live is, Andrew asked, why would people want to have small writing? And so one example of that is really just proof of concept to actually say, you know, we have the technology, we have the capability to try something new and do it to just advance science. Another thing is that long term, if we have this technology, this tool, then we can use it to, you know, arrange atoms or place things in a particular way to actually make new types of materials. So there's that. One other question we said is, how often is nano used? And fun fact, it's used a lot. And I think Ben can really address that a little bit more by talking about his research. So we'll do that. And one question we had is, what is a nanometer, which we covered, which is 1/1000th of a meter, really small. And then, is there anything smaller than atoms? And yes, there are subatomic particles, meaning smaller particles of atoms, like the electron, the proton, the neutron, and then even smaller beyond that, but we won't talk about that today, okay? But other than that, I will turn it over to Ben.
All right. So next slide, please. Yeah, so we're living in Silicon Valley, so we have silicon all around us. And in the top left is a picture of a stash of silicon wafers, which is the raw material on which we make all the computer chips and electronic chips that power our everyday lives. So yeah, so we make all the circuits on the wafer, and then we cut it up, we dice it up, and they go into cell phones and computers and everything that we use in everyday life. Next, please. Yeah, so the actual process of making these microchips is quite complicated, but you can think of it as, like, an analogy is like making a pizza. So you have a round pizza dough, and then you put several layers on top of it, but every now and then you have to pattern it and take out some stuff, and you add more stuff, like more toppings and whatever, and you bake it, and in the end, when it's done, you cut it up and eat it. Oh, not really. But you get the idea. So a clean room is where it's like a factory for making all these chips. So it's like, well, you have car factories and electrical appliance factories, but a clean room is dedicated to making items that have very small features. So hence the word nanoscale. We make nanoscale and microscale features. Okay. So the example, the research example that I will talk about today is connected with my work at UCSF, and it's under the guidance of Professor Shifu Roy. He's developing artificial kidneys to help with kidney patients all around the world. And the research is based on making nanopore filters, which is something you see on the right hand side here. Is very thin membrane, so you can see light through, so they're very thin, but they have very tiny pores in it. And next please. And they're designed to mimic the function of, at least part of the function of a human kidney, so that those poor kidney patients don't have to go to dialysis all the time, or they don't have to wait for a donor kidney, which is in short supply around the world. Next, please. Yeah, so if you take a human kidney and you zoom in, find it is a very, very complicated structure. It's amazing. So a kidney is about 10 centimeters long, right? But if you unfold all the surfaces inside it, you can see, you find that it's actually up to 1 square meter of nanopore filter area. So the function of the kidney is to let the blood flow through and take out, filter out all the unwanted molecules that should not stay in the body, like urea. And all the good stuff, like red blood cells, white blood cells, platelets, they are too large to pass through the holes in the filter. And so they stay inside the bloodstream and they go back to your body. It's kind of like a sieve, like when you're cooking pasta, you put everything into the sieve and you strain out the water and you keep your pasta. So yeah, we are trying to take advantage of high-tech technology here, semiconductor technology in the clean room, to mimic this filter structure, which is no easy task, but we're trying. Next, please. So, oh yeah, I just talked about it just now. So a kidney consists in large part of this porous membrane, which filters out the bad stuff that you pass out in your urine. And we're trying to replicate such nanopore filters in the engineering world. So the actual process is quite complicated, so we don't have time to talk about it here. But you can see that when everything is said and done, the membranes, so you look at the middle picture, this is a cross section. So you cut through the middle of the membrane and you use a scanning electron microscope, which Grace just described, and you really zoom in, and you can see that it actually consists of tiny channels, which are on the nanometer scale. So 7 nanometers, 10 nanometers. So yes, we can make such small dimension structures in the clean room. And when we assemble a lot of them together on a wafer, which is the one you see on the right, and then we cut them up into chips, and then we assemble them into another gadget. And hopefully we make these guys compact enough and dense enough and efficient enough, they can do the function of a regular kidney, and then we can actually implant them into a patient's body. That we have to admit is quite a few years away, but we're working hard towards that goal. And I want to also point out that so this research, or the field that I work in, although it involves clean room fabrication a lot, it actually does not result in an electrical chip. It actually results in a mechanical structure. So that's another major use of clean room technology, which is to make so-called MEMS fabrication technology, which is micro electromechanical systems. So MEMS actually powers a lot of useful items in our real life now, like accelerometers, sensors, the cameras that you see in a cell phone, and et cetera, et cetera. So here's a picture of some completed chips that we've made at Stanford, and we also make some at the Berkeley clean room as well. And yeah, so we dice up the wafer and we assemble the chips into a full artificial kidney. And Again, using the scanning electron microscope, we zoom very, very, very deeply in. And in the little inset picture on the right, you can start to see the little pores, which is pointed to by the two red arrows. And the pores themselves are only 10 nanometers wide. So yeah, they're pretty much very hard to see. But that is actually what the pores are in your actual human kidney. So just serves to show how amazing the human organ is.
Okay, thank you, Ben. I think we are transitioning over to the tour. So I'm actually going to stop sharing my screen and we are going to turn it over to Katie. I do have a question though, what I liked, and this is kind of more about Katie's research as what are those ultra thin transistors? Do they work as normal transistors or are they like quantum transistors or something entirely different?
Yeah, so that's a great question. So I'm actually about to show you guys one of the pieces here. They work kind of as normal transistors, but the thing is that because when you go to these really, really thin atomic layers, you get these really interesting quantum type effects that really change the properties compared to something that's really big and really bulky. So going just a few atoms is going to be a little bit different than if you go ahead and do something that's in bulk. So that's a good question. Oh, and then somebody else had mentioned on there about AI and nanotechnology. Did we want to cover that as well?
Yeah, go ahead.
Yeah, so something that's really interesting is, in order to perform AI, you really need to have billions and billions and billions of transistors in order to perform all of those matrix applications. So they make these gigantic 300 millimeter wafers that are bigger than my face in order to have billions and billions of transistors. So they absolutely work hand in hand. You know, you couldn't have artificial intelligence without nanoscience.
Awesome.
Yeah, so that was a great question. So I will start now showing you guys around. Oh, looks like my sample moved.
I have another question that I'll answer, which is how many particles per meter cubed in a clean room? And that's actually a really smart question as well. So there are all different types of clean rooms. Some are sort of quote unquote cleaner than others because a lot of clean rooms have different types of ratings. Our clean room here at Stanford is about a class 100 clean room, meaning that there are 100 particles per cubed meter. But there are classes of clean room that are down to class 1, meaning there's 1 particle per meter cubed. So that's a really good question as well. So ours is clean, but not too clean because some clean rooms don't even allow people inside because we, you know, as Katie will talk about a little bit more, are kind of, you know, the contaminants or, you know, the dirty parts of the clean room.
Yeah, so yeah, let's get started on that. So I'm going to share my phone screen instead. So you're going to see a little bit of double here. But so for the person that asked about the ultra thin transistors, this is kind of what we do in a typical research lab is we'll take different films that we've grown and by using all those different techniques that Grace talked about, like photolithography and depositions, we're able to do things like put down contacts in very specific areas in order to only probe this very, very small channel right here for those really, really thin transistors. So we do this kinds of stuff all the time with tons of different types of materials. Pretty much every element on the periodic table you would be able to find in a clean room. So moving along, so that was a microscope. Perhaps you have one of those in some of your maybe science labs in your school. So some of the different things that we do include...
Katie, really quickly, can you actually hold it vertically? Yep. It goes sideways. Okay, perfect. Thank you.
Is that better?
Yeah.
Cool. So this is where we do depositing of films that we can expose to light in order to pattern however we want to get little thin lines, or maybe you want little squiggles, or just depending on what it is that you're fabricating at the time. We also do a lot of work with furnaces and really hot things in order to go ahead and either anneal or make things hot, because properties change when you make things get a little bit hotter. This is what we use when we expose to light. So there's light that comes down and shoots down onto our wafers in order to expose the photoresist, which is the machine I showed you with the little film that you can put on in the spinner. And that is so that we can make our nice patterns.
And then another thing, Katie, oh, sorry, really quickly. I just wanted to comment on the COVID stuff where one of the attendees noticed that, you know, you were wearing a mask and another mask.
Yes.
Yeah.
Yeah, so, well, I'll talk about that then.
Okay.
So you can see here that I'm wearing a very interesting getup with lots of different interesting suits. You know, I have safety glasses, and then also I'm wearing a mask, but also this little net thing here. And that's because your clothes, your skin, your hair, anything that's on you is a huge contaminant for our materials. So little fibers from your clothes can get in. So these are special fibers that don't shed so that we don't get contaminants on our samples, because we are the biggest contaminants of our samples and not the other way around. All right, so moving out of the photolithography area, you're gonna see a color change. So we just went from yellow to kind of normal white light. So the reason that that is because if you remember, I was talking about how you expose to light in order to make your patterns. Well, if you have this nice white light, it's made of all the different colors of the rainbow. And so the problem with that is that you could just expose everything and ruin all of your work. And we don't want to do that. So we keep the light yellow so that we can keep all of our samples just how we want them to be. So here we have some big machines where we can deposit lights of metals and do what's called etching. So etching is where you selectively take away material either by shooting it with other ions, or maybe you use what's called a wet etch, which you use something like a wet bench here with lots of different chemicals that you can take away material selectively, or with those patterns that you were making. This is another one of those furnaces that I was talking about. You can see that it's so hot that it's glowing red there. These furnaces can go up to temperatures of up to 1,000 degrees Celsius. That's really, really hot. You're not going to get that in your oven at home.
Okay, so I have a few other questions. Oh, when you closed the door, didn't you let millions of particles into the clean room? Yeah.
Yeah, so this is all in the clean room. So we have doors and all this normal stuff in a clean room because, and actually right by it, we have this little area back here. It's called the gowning area, where you put on your gowns and clothes all over your clothes so that you don't get it in the main clean room here, which is segregating from the rest of the building.
There's actually a special procedure for you to put everything on, and there's a certain order, so you're minimizing any sort of contamination and things like that.
Yep, absolutely. Yeah, so another really important thing is I was just talking about how there's all these dangerous chemicals in here. So we have things like showers and eye washes. So just in case we get dangerous chemicals on us, that some of them can even eat your bones, so that we can wash off and make sure that we're safe, even if there is an accident. Even though we wear tons of protective equipment and safety glasses and extra aprons and face shields and tons of other stuff, accidents can still happen. So we have to make sure to be safe.
And again, you know, a couple of people are asking about coronavirus research, and then how are we safe in corona. So actually, when COVID hit, all of our labs actually shut down, and it took a while for the staff to work and adapt the lab to make sure we are safe. So there's policies in place, like for example, Katie is wearing a mask. There's social distancing rules, and then even we had to rearrange some of the parts of the lab where it might have been too close, because you can see here, you know, there's so much stuff. There's so many tools inside of the lab. Some of the tools had to get moved around so people weren't being, you know, too close together and sort of being unsafe. And some people are working on technology for COVID. I don't know it in particular, but maybe Ben, I don't know if you can comment on that, or Katie, or even Grace.
Actually, as a matter of fact, although our current work is stemmed from making kidney filtration chips, it can be adapted to make filters for the transport of oxygen between blood and air. And also, so you can adapt it for use in ventilators. And also there's something called ECMO, extracorporeal oxygen transport, I think. So yeah, we are adapting our technology to various other applications that have a relevance to COVID treatments.
And I will say that at Stanford, there are several amazing researchers and professors who are investigating ways to help tackle the COVID problem. Off the top of my head, I know that Sarah Hailshorn in the materials department is working on ways to help deliver vaccines or drugs to help fight against COVID. Manu Prakash is also looking at ways to identify antibodies for COVID, the COVID virus. And in the Stanford Medical School, a lot of researchers are really diving into how COVID works and ways to fight against it.
Great.
Yeah, and even in departments like environmental engineering, they're studying how long things can last on surfaces. So it's all really a multidisciplinary, all hands on deck effort.
We have a few more questions. Someone noticed that there was popcorn.
We're not allowed food in the lab.
Yeah,
so,
no food in the lab.
Yeah, I don't think it was popcorn.
I'm trying to answer as many questions as possible. We have one, I really like this question. Why don't we measure things in a sort of quote unquote universally sized atom and measure things in nanometers? And is it because we can't see atoms and we can only see the sort of aura they make around themselves? That's a tough question, I think.
Yeah, I guess I'm going to answer the why do we do things sort of in a standardized way. And so think if you're talking to your friend and you say, oh, well, I have 5 bunnies at home. And your friend says, oh, I have 4 cats. But really, you're both talking about the fact that you both have 5 popsicles because you're using different words for the same thing. So that's how we make sure to standardize everything that we're doing so that a scientist in, say, Switzerland is able to understand what I'm doing as well as the reverse.
Thanks, Katie.
Hopefully that kind of answered the question.
Yeah, I think so. Let's see. Does anyone, okay, let's see. Any other questions? Can you manually fight viruses with nano robots? I saw the chart viruses was on the same level as nano robots. So I don't know if we actually have developed a sort of nano robot on the same size and scale as a virus that is that advanced. There is research when it comes to like developing types of nanoparticles or smart drug delivery systems that can do that, but I don't know if they can sort of manually fight them. I would say it's more like they can target certain parts of the coronavirus or, for example, cancer to then send the nanoparticles or send the specialized drug to that area to target it, but not necessarily it's a mechanical, physical thing. And obviously anyone can answer as well.
Yeah, I mean, I guess that fighting the COVID viruses, you have to fight on the same scale. So it's on a chemical scale, it's on a biological scale. So nano robots are actually still larger than that scale, but they can be used to deliver the agents, the chemical agents, biological agents needed to fight the virus.
Okay, and yeah, thank you. And any other questions? Otherwise, Katie, maybe do you want to walk back around to the yellow parts? I don't know.
Yeah, sure.
Yeah.
Yeah, I guess there's a couple more things maybe that they can see, like the atomic layer deposition. So another really cool thing that we can do is we can deposit atom by atom, which is quite exciting. And then one other thing to kind of point out is all of this piping back here. So we have tons and tons of different pipes and exhausts and tons of gases that we can use and lots of vacuum systems. So there's a lot of different things that we need in order to make sure that all of our instruments are running. So we go through a lot of nitrogen, a lot of argon, as well as tons of water to keep all of our equipment nice and cool, because otherwise it could overheat.
I have a few more questions. What would be the minimum size for a nano robot or nanotechnology?
I guess the fundamental answer is one atom, maybe. I guess I don't personally work on anything related to nanorobots, but that's kind of, I guess, the fundamental limit of everything is just one atom.
Okay, I have another good question. What is the foil for? I think he was talking about the maybe Fiji or.
Yeah, I think the Savannah has foil on it.
Yeah.
Yeah, so there are several different reasons that we use foil in the lab. One of them is it's pretty simple. It's so that we don't get things dirty. But some of the other reasons that we can use it are to dissipate heat on some of our instruments, because even the water cooling, sometimes that's not even enough in order to keep our instruments cool. So we use maybe different metal foils to keep it clean, or even just, so that you can change it out so that things don't get contaminated on the different tools.
Okay, and then I have a good question by Wei Min. Do the properties of materials change at such a small dimension, such as say copper, iron, or silicon?
Yes, absolutely. Yeah, so that's actually kind of the basis of at least my own work, is that, so I work on a material called indium selenide, and in bulk, it is very different from when it is in this small nanometer scale. Some elements and some different compounds can go from maybe metallic when they're really, really big to maybe they're a semiconductor when they're really small. So those interactions between different electrons and different atoms in the system are really important for the ultimate properties. And if you remember with what Grace talked about, the different colors of gold with the different film, those change quite a bit if you saw those with the nanoparticles. That's another example of how nano things can really change the properties of from bulk to small.
Awesome, thank you. And then actually I had a really question, but for some reason it might have disappeared, but talking about their career paths, like how would someone get into nanoscience? And what is really nice is that actually we have people from all different levels of learning. So Grace is actually an undergraduate, and then Ben is a senior researcher, and Katie is a grad student. So I don't know if you guys want to talk a little bit more about that too.
Yeah, I can get started. I answered that question, but you can have people from all different sorts of fields. So if you're interested in STEM and you really want to work on cutting edge technology, then that really will help lead you into the nanotech sphere. So we have a lot of people coming from chemistry backgrounds or physics, bioengineers, people interested in material science or double E. So it's really, as long as you stay curious and you're interested in you applying material science for something, then you can study it in college and then work in that field.
Okay, thank you, Grace. Sorry, it's hard to manage all the questions. Okay, another question is, could you use ultraviolet light to clean the clean room? Anybody want to take that question?
So the question was, do we use ultraviolet light, correct?
To clean the clean room, but we do use UV light for something else, yeah. And I'll let Katie explain.
Yeah, so I was just going to add on, we use UV light for that, but also we use UV light for lots of different characterization methods as well. So you can maybe probe different materials and see what kind of light shoots off from them in order to see what characteristic stuff every single film has. That's often done with UV light. There are other applications. I don't know if Ben and Grace maybe want to add on.
Well, I guess maybe I'm guessing the intent of the questionnaire is like from a biological point of view. Yeah, a clean room is, I guess, intuitively not a biologically dirty place, at least no more dirtier than the outside world, definitely, because everybody's wearing gowns and masking up and everything. So yeah, typically people don't use like don't bring in a big UV machine to disinfect a clean room. But the clean room, by its nature, because of the humans in it or things being brought into it, still has a background, a few remaining particles which can contaminate the devices that you're making. So for that purpose, we circulate the air a lot through so-called HEPA filters, which is very highly fine-grained filters, so to speak, that traps all those tiny particles. So the end result is that the air inside a clean room is both particle-free, clean, and also, we hope, biologically clean.
Great. Okay, so let's see if any other questions. So how many particles does it take to make nano? Is Emiliano's question. I thought that was a cool question. I think, so yeah, there is something to be said about how much material does it take for something nanoscale to be nanoscale. I would say like tens of atoms, because there are people that are trying to do like quantum computing, like single atom computing, but you do need to have a certain amount of material to make it nano and for those nano properties. It's almost like Goldilocks and the Three Bears, where you have your bulk material, which means, it's too big. And then something that may be single molecule or single atom may be too small, whereas something for nano is kind of this just right size where all these unique properties are happening that we're trying to take advantage of. I hope that answers your question. And a few other questions. Have there been any experiments significantly messed up from contamination? Katie's
all
nodding.
The time. all the time. Yeah. More often than not.
Yes, okay. I guess historically, when people started, like 50 years ago, when people started to develop the electronic industry, they did not know that particles and contaminants could ruin their work. So they kept having trouble getting the devices to work. And eventually they looked under the microscope or the scanning electron microscope, and they figured that the particles that swamp, or they actually dwarf the devices they're trying to make. And they crush them, they prop, they create gaps in between layers. And so that's what's ruining it. So eventually they realized that the whole room, the whole factory, has to be sealed inside the compartment with high efficiency filters to make the air special clean. And that's how the clean room came to be. And yeah, as Angela said, the most advanced clean rooms now don't even allow humans in, or if they allow them, they may have to put on a whole spacesuit with their own breathing system, just like the astronauts.
A few more questions. I don't. Ben, did you want to have time to show some of your devices off, by the way?
Yeah, just a minute or two.
Okay, let's do that really quick. And then again, if anyone has more questions, I know we only have like 9 minutes left, but yeah.
Yeah, so this is a mock-up, a model of the artificial kidney. So remember the chips that that I just showed. So we fit like a stack of them inside here, and we make some channels in and out of the kidney, and the blood flows in, and then the urea flows out. And hopefully, if we can make it small enough, it can fit inside the human body and be an artificial kidney. So we don't have to get the real donor kidney. And obviously, the thing about you have these iPhones now, and they're actually as powerful as like mainframe computers some 20, 30 years ago. And those stuff, they took up a whole room. So the name of the game is to keep miniaturizing them, making them smaller and smaller and smaller, and packing more efficiency into it so that they get small enough that they can be implanted into a human body. And then I think, yeah, just one more thing to show. So Katie, I know she showed a super duper huge wafer. So this is another. This is actually yeah, a prototype kidney chip wafer. So it's very hard to see on the screen, but you can, if you cut it up, you can get 5 chips out of it, and then we can put that into a device. And I guess, yeah, that's all I need to show today.
That's good. Oh, somebody asked, won't it be uncomfortable inside the human body? I think the prototype right now.
Yeah, I think the initial approach would be to have tubes come out of the body and attach to like a small backpack that you wear or something, like maybe this size, and then you just carry it with you. So it won't actually be like a big, like a chunk of metal inside your body. So, but I'm talking about like eventually, just like iPhones or phones became smaller and smaller and smaller, eventually, who knows? Maybe 10, 20 years from now, they can be small enough.
Yeah. Yeah, if they would replace the kidney, but I guess you kind of answered that there would be tubes. Another person asked, are there any animal studies yet?
There are. I'm not the best qualified person to talk about that part of the research. We have specialized biologists and doctors in charge of it. So far, we haven't tried it on a human yet. It's quite a daunting challenge because not only have to make sure we have to make sure it's safe to test it on humans, but you have to go through a lot of regulations, a lot of approvals, and also due to COVID, a lot of research has been slowed down. So, but we are actively working towards testing in humans. And yeah, we actually have a web page that you can follow, kidney.ucsf.edu, and you can see more details about it.
Yeah. Okay, a few more questions. One is why, as very simple, I like this question. Why do we have computers in the clean room? Is what Emiliano is asking.
Maybe Katie or Grace.
Katie, do you want to answer that?
Yeah, I can answer that. So the main reason is to do things like the images that I was showing you on the microscope so that other people can see them. We have computers to control some of the equipment that we have in here. So we use a computer to control the photolithography. We have computers just to sign in and out partially because of COVID, we do have to limit the number of people that are in the clean room at a time, as well as we have to reserve tools so that 4 people don't show up at the same tool and want to use it at the same time.
Awesome. And then, all right, so that's a good one. Oh, I like this question. Have you ever made an accident in the lab that turned out to help towards your goal or gave you a different one? Yeah, everybody's laughing.
Trying to think. You guys?
I like to joke that some of my best growths are actually my Hail Marys, which is where I do crazy stuff that sometimes it just ends up working.
That's, I think,
I say that, but it comes with some background knowledge too, so you can't just, throw some things together and hope for the best. But with some knowledge, have happy accidents.
Yeah, I think there's a lot of happy accidents that happen, but there are also some, like really things that you set up and you take a lot of time to work, and then it totally goes haywire. So I think it's always a mixed bag when it comes to research, which is why I think a lot of people like research, is sometimes you never know what you're gonna get. Yeah. Okay. Can you control the oxygen in the clean room? Oh, and another question, a UV light projecting drone would be a good idea to clean the room more effectively.
Well, it's also harmful to humans, so you have to make sure that nobody is in there while you're doing it. So yeah, maybe you can send one in in the late hours and clean everything.
Yeah. And then, but we would have to be careful because especially in the area where Katie is, where it's yellow, the light, the UV portion of the light spectrum is removed. So we don't want to spend the drone around there because then there might be some, samples exposed, things like that. A couple other questions. I know we're nearing the time. Denise asked, do you ever isolate atoms of gas elements? So yes, I would say. I don't know, Katie, did you want to answer that?
Yeah, I can. So if you were looking at those gas lines that I showed you, we isolate those gases so that they're nearly almost atomically pure, because otherwise they could contaminate our samples. So for example, some things oxidize, so they change chemical structure, and we don't want that on a lot of our stuff. So we make sure to separate out the atoms that we want.
Great. Thank you. Okay. And then Renzao asked, have we progressed enough on nanomachines to entertain dedicated power sources at that scale, or are passive devices the only practical thing right now? And I think along with that question, someone else asked, when do you think nano will be as small as a virus or a DNA? for anybody?
So I suppose nano stuff is already as small as kind of viruses and DNAs, right? So I believe Angela had an image at the beginning that showed kind of the scale of DNA, which I think was around 10 nanometers or so. So for example, the thickness of some of the stuff that I showed you is about 1.4 nanometers. So it's actually thinner than DNA. Somebody else want to answer the nano machines? I'm not super familiar with nano machines.
Well, I guess in a sense, there's a lot of overlap, right? It is a matter of how you name it, because nano is pretty much close to atomic scale. So if something is grown naturally or occurs naturally or like is produced chemically, then people call it a chemical, right? But then if you make it in a machine, you stamp it, or you somehow artificially force its dimensions to be that small, then you call it nano. But in a way, nano at a certain point becomes chemistry, and chemistry at a certain point, you can call it nano.
That's good. Shan has a question of, if HEPA filters are used to clean the clean room, shouldn't it make it safe from the COVID virus? Yes and no, because yes, it will filter all the air, but that depends. If there's someone who has COVID, they could expose somebody. So you always have to be very careful. Everyone still has to wear a mask. Okay. And then a couple other questions were at the time, but I just want to say thank you everyone for staying on and talking to us and listening to us. We'll probably end pretty quickly, but there is also a survey. So if you can take the survey at the end of the webinar, we would really appreciate it. It helps us improve the webinar or the tours and things like that. Okay, questions. Do you guys work on creating artificial tissues or graphene powered circuits? I'm gonna just say yes. How does CRISPR relate to nanotech? Does anyone want to answer that?
I'll let you guys do it.
Okay, so CRISPR relates to nanotech in the sense that it is the size and scale of nanotechnology. It may not necessarily be specific to nano, but I would say it's more like nanobiomedicine. And so there are all different types of treatments that are within like cellular therapies and things like that. They're all kind of related. So although they're primarily biology, they're still nanoscale, but maybe not necessarily nano studies. And then some people are asking, if somebody is interested in staying in touch with Nano at Stanford and learning more, go on our website, email me. I think my email is listed, or any of us, just to ask questions. Some of the nanotechnology, yes, can detect COVID or types of COVID testing. There's all different types of tests being created. I'm sorry trying to answer all these questions live, but we are at 2:00. Did you have to wear a mask before COVID? That's a great question, David. And technically, yes, it depends. So most people did not wear masks, but some people that had beards would wear a beard cover. That's actually what Katie is wearing on top of her mask, because her mask has particles because it's made out of some type of cloth, which could shed. But so we want to be careful with that. So then they wear an additional mask on top of that. Okay. All right. Anything else? We are at the time. So just please stay in touch. Our website is nanolabs.stanford.edu. So if you have any questions, you can contact us. There's emails listed on there. Otherwise, thank you all for your time. And yeah, we will close it out. Okay. All right. And then thank you, Ben. Thank you, Katie. Thank you, Grace. Yeah, round of applause. I know they can't see or hear you, but
hopefully
anyway.
next year we can meet in person again.
Yeah, someday hopefully we can do this in person. All right. Anyway, have a great day, everyone. See you later.
Bye.
Bye.